Good morning, amigos de la geometria. Good morning, geometry friends. We got another exciting problem here today, posted on 8/7/2026. Okay, we have learned that the exterior derivative, little d, acting on a zero form gives a one form, the gradient. Now we want to study what the exterior derivative of a one form is, okay? Before going on, let's step back to vector calculus, which we're all pretty comfortable with. Okay, we have a function. To find the vector calculus method of the gradient, we know how to do that. So the del operator acting on the function gives this, and here's the answer, right? Now we want to take the curl of this gradient, right? So del cross del f, and we know how to do that too. So here's our setup, and here's the vector it forms, okay? Now, you can tell real quick, this is 0, this is 0, this is 0, this is 0. They're all 0. And you're saying, what, you big dummy? We all know that. The curl of the gradient's equal to 0. Why'd you do this? Well, I'll show you in a minute. But anyway, after doing this, because I knew the answer, I thought, what is the geometric concept here behind the curl of the gradient equals 0? I actually never thought about it before. So I got my toys out here. So this is our function, right? And we're projecting our level sets here in this XY plane. Now remember, these level sets are a projection. These contour lines are actually all over this manifold, yes? But either I can't do it in Desmos or it won't let me. I can't make this on here. So this is the best I can do. So what I've done here is put a gradient vector starting at the origin that is lined up with that point, yes? So as that point moves up or down, you can see that that gradient vector that's at the origin, it 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 punctures more or less of these contour lines, which are our one forms, remember, or not, right? And of course, it also goes around. Okay. So when we take the gradient, we are at this point and we're saying which way is the direction of steepest ascent or descent, depending on what we're doing, right? But what happens when you take the curl of that you've just done? You actually want to measure the circulation, right? Which means what? It means you're studying this. You're just walking around the mountain at the same elevation at all times. You're not going up or down, right? So that's why it's 0. I actually never even thought about that before. Okay, that's not the point. All right, now we've done that. Now let's take the same function and use differential forms like we've been doing. Okay, so here's the punchline. The exterior derivative of a 0 form gives a 1 form. D acting on a 1 form gives a 2 form. D acting on a 2 form gives a 3 form. And you can go as high as ever how many dimensions you got. And we're still at 3. Okay, so here's our manifold. We take the exterior derivative acting on the function, and we know how to do that by now. Okay, now let's do it again. So we're going to say the exterior derivative acting on what we just did. Okay, so it distributes like this. These are products, yes. We have to use the product rule, so we get 4 terms. Okay. Now, some magic occurs, and you get that this and this are both equal to 0. Now, the actual mathematical proof of this is, I don't understand it. Here's the way I understand it. When you perform this operation, you're going to wind up with this. That is a 0 form, right? And you're differentiating it twice. You're going to wind up with a second derivative with respect to these two coordinates. plus this wedge, the product, right? Now, we know that the order of differentiation doesn't matter. So on a smooth manifold, so I can go I first and then J, or I can go J first and then I, right? So these two things are actually equal. Well, these two things are not equal. This commutes and this anti-commutes. When I swap these, I pick up a negative. So what's that mean? That means that this is equal to the negative of itself. And the only way that's true is if it's zero. Okay, this is the simple P-brain way that I understand this. If you know a better way, please jump in. Okay, so we have done this and we said those are zero, so we're only left with these two things. Now, we're taking the exterior derivative of a zero, the form here. So we're going to make a one form. There's our one form. We're going to make another one form. All right, so let's distribute. This is why we did all that wedge product stuff that was so boring, right? Because we know we can distribute this wedge now. Okay, so let's distribute it. So we're going to get this dx wedge dx, this wedge dy wedge dx, this dx wedge dy, this dy wedge dy. Okay. What's this? Well, that's 2. What's dx wedge dx? 0. Anything wedged with itself is 0. What's this? That's 0. What's this? 0. What's this? 2. dy wedge dy is equal to 0. So the whole thing's equal to 0. And this is called nilpotency, which which is a word I've never heard before. I had to look it up. So this is word of the day. The word nilpotency comes from the Latin roots nil, which is what they use in soccer when you don't score, which is most of the time, and potens, meaning powerful or having power. Literally translates to having zero power. There you go. Word of the day. All right. Back to our problem. All right. So we said the curl of the gradient is equal to 0, and the D operator acting on the D operator acting on a function is equal to 0. This is a gradient, yes? Well, is the 2 form the differential geometry equivalent of the curl? Is that what that means? All right, here's the problem. Take the exterior derivative of the 1 form. So I'm giving you a 1 form. Take the exterior derivative of that 1 form and compare it to the curl of its equivalent vector x dy minus y dx. Okay, I'll post the answer tomorrow. See you later.